really nice to really nice to be here with you guys. And so let me tell you right away that this work is collaboration with my PhD advisor Pavel Lushnikov at University of New Mexico and Michael Sigel at New Jersey Institute of Technology, who I got acquainted with when I was at Courant, because it's just 1 hour between the Courant and New Jersey Institute of Technology. So we worked on a few projects, including this one. So here we're looking at the Constantin-Lax-Majda equation, and let me tell you right away what this equation is. So basically, the motivation is to analyze some simple model that describes or models the situation similar to 3D Euler equations. So basically, if we start with 3D incompressible Euler equations in vorticity formulation like that, these equations are quite complicated to solve or analyze analytically, or even if you attempt to solve them numerically, it's pretty difficult task. So the idea that ConstantinLax-Majda had in 1985 is to reduce this equation into some simpler equation, some model, some one-dimensional equation that you can actually analyze in terms of, for example, complex singularities and their movements, and try to judge something about the singularities in the original 3D Euler equation. So in the original 3D Euler equation, if we write it in vorticity formulation, we have this omega, which is a vorticity of velocity field u, and we have this advection term and this nonlinear term that we call, or that is historically called, vortex stretching term. And this term, if you look at it, basically it scales as omega squared, because here we have one omega, and in this grad of u we have another omega essentially. And this term gives us basically formation of singularities if they ever form, whereas the advection term cannot make omega grow. So this advection term basically is stabilizing term. In R3 space, basically, if you solve it, so in this equation, we have a relation between u and omega through this vorticity relation. So we can express u through omega like that, but solving this equation will depend on boundary conditions. So in R3, for example, that becomes the Beer-Savart law, like so. So basically, u is expressed through omega through this singular integral operator, and which is proportional to omega to power 1. Okay, so basically, when we simplify it to 1D model, what ConstantinLax-Majda did, they just completely omitted this advection term, and they left only the vortex stretching term, the second one on the right-hand side. And basically, they left it in a form as omega times ux with partial derivative of u, and that ux, previously, instead of ux, we had grad of u over here, and that was expressed through some operator s of omega. And this s of omega is basically integral singular operator, similar to this integral over here, that depends on omega linearly. And in our new formulation, this u of x will be expressed through Hilbert transform of omega, which is very similar because it's also linearly dependent on u. It's also integral singular operator, and many of its properties actually match the properties of this more complicated matrix singular integral operator in the original Euler equation. So in a sense, they have a lot of similarities, but this equation is much simpler to solve and analyze since it's only 1D model, and this Hilbert operator is also very convenient to work with in many respects. So analytically, it allows certain kind of manipulations, and also numerically, when we compute it, for example, on periodic domain, it's very easily computed on periodic domain through Fourier transform, because Hilbert operator is simply I sine of k in Hilbert transform in a Fourier space. So this equation over here basically was original Constantin-Lax-Majda equation that we call CLM equation. We looked at the more general case where we actually keep that advection term or transport term, as we call it, and we also put a general constant A in front of it, which will basically set up relative strength of this advection term relative to this vortex term. So this is the main equation that we're going to analyze here, and we done mostly many numerical simulations to analyze different types of solutions of this equation. And in this equation, again, the U is expressed through omega through this relation. Ux is equal Hilbert transform of omega. Okay, so here are some historical references. Let me go through them before I talk about our results. So basically, originally, Constantin-Lax-Majda considered A equals 0 case. And for that case, they established finite time singular solution for that has a finite time blowup. I'm going to show you that solution a little bit later because it could be written out analytically. So that's quite educational to look at it. And then later, de Gregorio considered the case A equals 1. So basically, A equals 1 is the most interesting case from the physical standpoint of view, because if I come back here, this advection term in Euler's equation also comes in with the coefficient A equals 1. So A equals 1 corresponds to Euler equation the most, kind of. And other A's we just consider to kind of to see what other behaviors we can get out of this equation, but also in few other applications we could see a similar equation with A equals -1, I believe. Okay, so later on, Akamoto, Sakai, and Wunsch also considered a few cases. They proved global existence for A equals 1 on, I believe, real line, and conjectured finite time singularities for A less than 1. And they showed global regularity for A greater than 1 for domain that is periodic, and x goes from -pi to pi. So here it's important to mention also on what domain we work. So there are two cases people typically consider: the periodic domain when x goes from -pi to pi, and the whole real line when x goes from -infinity to +infinity. And sometimes the results of two of these cases are the same for the same A. Sometimes they are different. So it's important to distinguish them. So here again, I laid over some historical references on the number line for A, and we're going to use this picture as a reference. So basically, here I point out everything that's been known before we started our investigation. So basically, for A less than 0, it's known that this equation has a finite time collapse for any A less than 0. For A greater than 0, what's been known is that for x on a real line, we have a finite time collapse for small a's. So at least it's been proven recently that for small a near zero, we have finite time collapse. It's been also known, well, originally for a equals zero, but now it's been proven for small a's over here. Then recent results that we also discovered while we were doing our studies, that for a equals 1/2, Chen found a self-similar collapsing solution right at this point, a equals 1/2, but they did it through some analysis, which is different from our analysis. So we kind of found it in two different ways independently. We also found a solution for a equals 1/2, and I'm going to show it to you as well. And then for a near 1, there are some results as well. Let me just point out again that there are two cases that I'm showing on this number line. On the upper half, I'm showing the case for x on a number line. Below, I'm showing results for x on a periodic domain from -pi to pi. And as I said, a equals 1 is the most interesting case. What's been known is that for real line case for a equals 1, there is a stationary solution over here. And it's also been known that there is expanding compactly supported self-similar solution if we work on a real line. Now, if we work on a periodic domain, it's been known that there is a finite time collapse if a is a little bit less than 1, and there is a global regularity if a is greater than 1. Okay. And also, what's interesting for a equals 1, for periodic case, there is a global existence, whereas for real line case, there is actually expanding compactly supported self-similar solution. So there is a blowing up solution for a equals 1. So it's quite different for these two cases. So now everywhere I put the question mark, these territories were not explored very well. So that's why we did many numerical simulations to sweep this parameter A and to explore all kinds of solutions that we can get in this range. We did sweep through all A's, regardless whether it's been explored or not, but these are the most interesting regions that we were looking to find answers for. And here's kind of a summary of all of our numerical simulations. I'll explain it in detail, and later on I'll show particular examples of simulations. So first of all, I want to distinguish what we call blowup and what we call collapse. So blowup is just the divergence of amplitude of the solution in time. Typically, we look at the finite time blowups, whether it happens in a finite time or not. And collapse is the same as blowup, but additionally, we require that the spatial extent of the solution shrinks over time. So basically, if I say finite time collapse, that means the solution not only increasing in amplitude to infinity in finite time, but also shrinks in horizontal extent.
Dennis, can I ask a question?
Yeah, sure.
So you're not, I guess I'm confused that collapse includes divergence of amplitude. You could also just have the support of the solution shrinking without divergence. Is that
yes, but here typically, if we have a collapse, it's both shrinking and the amplitude goes to infinity. So we never observe the case where it shrinks but does not go to infinity in amplitude.
Okay, thank you.
So these two cases were enough to cover all the kind of blowing up solutions we have. So what do we have here? Again, here's the number line for A going from minus infinity to plus infinity. And on the upper side, I show the real line case when X belongs to R. And below, I'm showing the case for periodic domain from minus pi to pi. So as I said, historically, it's been known for both of these cases, when A is less than 0, there is a collapsing solution. And we did observe that for both of these cases. For A less than 0, there is a collapsing solution. And more than that, it's not only collapsing, but it's also self-similar when it's collapsing. And that self-similar form could be expressed as follows: omega equals 1 over tau, where tau is the difference between the TC collapse time minus T. So that's a positive time that is left before the collapse occurs, and times some self-similar profile F that depends on X over tau to the power alpha. And that alpha is different for different A's. So, and it turns out that, well, for the periodic case, it's the same. It's the same shape of the self-similar solution and the same alpha, basically. But what turns out, these collapsing solutions could be extended beyond A equals 0. And they could be extended all the way up to the special value of A that we call A critical. And we found this value with very high precision. We found it actually up to 15 digits, I think, after the dot. And after that special value, now we start seeing the difference between the real line case and the periodic case. For the real line case, we see expanding blowing up solution. So basically what it means is that amplitude goes to infinity, but then instead of shrinking, it expands. And when we're on a real line, basically it's free to expand as far as it can, as it wants, right? Whereas on the periodic domain, it initially starts expanding, but then since we have a finite, well, we have a periodic boundary, and it's a finite size of the domain, it cannot expand infinitely. So it originally starts expanding, and then it hits the boundary, and those kind of sides start filling each other, and then the expansion slows down and basically stops, whereas the amplitude keeps growing. So we also have a blowing up solution, but basically this expansion is arrested in the periodic case. And the self-similar profile in this case for real line, it has the same form. The only difference is now alpha is less than 0 now, and that the sign of alpha being less than 0 actually indicates that expansion instead of shrinking. Whereas for periodic case, when the expansion is arrested, then the self-similar profile is very simple. It's just some function f of x, and alpha is essentially equal to 0. There's no expansion or shrinking at all happens. It's only amplitude that grows to infinity when tau goes to 0. Okay, so after that, basically, then we have this case A equals 1. I'm gonna tell you about these gaps a little later, but basically now the interesting case A equals 1. For real line, we observed expanding blowup solution of the same form, whereas for periodic domain, we observed global existence, as it's been predicted by a few other papers before, as I said. And then beyond 1, basically we have global existence, and for both cases. Now, let me tell you about these gaps. So basically we did numerical simulations for all of these A's, and everywhere we were able to come to kind of conclusive results, except for this couple of gaps where our numerical method that we chose was not very appropriate, and it was basically struggling to give us conclusive results, but we kind of sure that these results extend over this gap. It just, by our numerics, we could not show it very definitely. Whereas we're sure that there is no kind of special cases, and basically if there's global existence for a greater than 1, it also covers this gap. It's just we should have changed our numerical method slightly to cover this gap, but we just didn't have much time for it. But we're sure that there is no more like special cases in here. All right. So on top of this investigation of this time-dependent PDE, what we did as well, we also found this self-similar profile F for certain A's. And we were able, so where you see the green line, basically we were able to set up eigenvalue problem and actually solve for this alpha and solve for the self-similar profile F with very high precision everywhere where we have green color. And so basically it extends from -infinity for A all the way up to some quantity here around 0.95. So I'm going to show these results, but let me start. Let me show you a few solutions for different A's, starting with A equals 0, and then A equals 1/2, 2/3, and greater than 1. Okay, so first I'll show you the classical results from Constantin-Lax-Majda paper from 1985 when A equals 0, basically. In that case, we can solve the solution and we can solve the equation analytically by simply splitting the solution into two parts. Omega plus, which is analytic in the upper complex half plane, and omega minus, that is analytic in the lower half plane. In that case, the Hilbert transform of such omega can be computed really easily. And it could be computed in this form. If we plug it in, basically we can separate the omega plus and omega minus part, and they just split in two ODEs that we can simply solve. And here are the two solutions for omega plus and omega minus. If we put them together, we get the following solution for omega, which has a finite time singularity if few conditions are met. So if you look at this equation over here, if, for example, omega naught is equal to 0 at some point x, then this term goes away. Now, if this term becomes 0 at some point in time t, then basically denominator turns to 0, and then you have a collapsing solution. So when does it happen? When, for example, h omega naught at some point is positive, and at some time t, this term could turn to 0. So if these conditions are met, omega naught is equal to 0 at some point in x, and h omega is positive, then you have a collapse at positive time t. So now if you want to get a self-similar form of the solution, we can do the following. We can consider this case that I was just talking about. Assume that omega naught, the initial condition, has a 0 at some point x naught. And here you can actually compute the collapse time, Tc. And then we can tailor expand this solution around x naught and get the terms up to Tc minus t to the power 0. We can get the solution in this form, and we can form a self-similar variable xc that is equal x minus x naught over Tc minus t. And if we neglect this other higher order terms, we can rewrite this part of the solution as follows over here. And turns out that this solution by itself is exact analytic solution of the CLM equation. So if we just plug it in, turns out this solution is actually exact solution. And here omega plus and xc plus and xc minus are just some numbers that depend on the initial condition omega naught. And as you can see, the time dependence here is like 1 over Tc minus T. So when T approaches Tc, we have a collapsing solution. The amplitude goes to infinity. Xc is self-similar variable. So as you see, when T approaches Tc again, this solution shrinks. And if you look at this solution from the standpoint of singularities, basically it consists of two simple poles, one simple pole at xc plus and one simple pole at xc minus. So basically it's two simple poles approaching the real line as t approaching tc. And so basically looking at this solution, we got inspired and we wanted to analyze all the other solutions from the standpoint of complex singularities. And so here's our general approach for
analyzing. Another question?
Yeah.
On the previous slide, you said it's two singularities approaching the real line as t goes to dc.
Yeah.
But the pole locations that you have below doesn't seem to depend on time.
Well, so xc plus and xc minus, yeah, they don't depend on time. They are constants. But if you look at xc, it's made of x minus x naught divided by t minus t. Okay. So if you think of in a space x, right, these locations, well,
so in the physical variable,
yeah, in a physical variable x, this is going to be two simple poles approaching the real line.
Okay,
in space c, of course, that's two points that are not moving, but that's a self-similar variables. Yeah.
Thank you.
So, okay, so inspired by this, we thought, okay, let us analyze all the solutions for other A from the standpoint of complex singularities. And let us assume that the singularity structure, at least the main singularities that are closest to the real line, are given by two branch cuts. So branch cuts are more general than poles. Poles would be the particular cases of branch cuts, and in general we'll assume that we have a branch cut with certain power on each side of the real line, and these branch cuts would start at a point I times vc that depends on t. This location vc would depend on t as a function of time, and on the other side we would have a symmetrical branch cut with minus ivc. And we can basically write our solution, or at least ansatz, assuming that the main contribution comes from these two branch cuts with the power gamma. We can write this ansatz in this following form. Some coefficient that depends on t divided by x minus ivc that depends on t with the power gamma. That power gamma would indicate the power of our branch cut. And then we would add another branch cut that is on the lower half plane, given by this term, and then some lower, less singular term. So plug in this ansatz in the original equation with both terms, advection and vortex stretching term, give us the following result. We can establish the dependence of this gamma on A. So if we plug it in and compare or balance the terms with all the most singular terms, then we can establish that gamma depends on A in the following form. And in fact, we did many numerical simulations and confirmed that this dependence actually takes place numerically. We confirmed it with very high numerical accuracy for at least for A between 0 and AC. I think it's also actually valid for negative A's as well. So here a few interesting cases happen. In general, gamma, some general number gamma gives us a branch cut, but for particular a's, gamma becomes integer number, and that makes our singularity a pole of certain degree. So for example, when a is equal to 0, the case that I just showed, gives us gamma equals 1. That's a simple pole. A equals 1/2, that I was talking previously about, gives us gamma equals 2, which is a pole of degree 2, double pole. And that's another actually exact solution that we can find and write out analytically. And a equals 2/3 gives us gamma equals 3. That's a pole of 3rd degree. This solution, though, cannot be written out analytically, because on top of the 3rd degree poles, we have additional singularities that is hard to take into account. Those additional singularities are branch cuts. They are further away from the real line, but they present in that case. I'll show you the picture later with those singularities. And any other a from 0 to 1 basically gives us non-integer gamma, which corresponds to 2 branch cuts. Again, in some cases, these are the only singularities. In some cases, these are the kind of the main singularities that are closest to the real line, but there are additional ones that we're not taking into account. So that's why this is only the leading order terms, whereas other terms also might be present. All right, so this is our approach. Also, when we look at the solutions, sometimes it's also helpful to write them out in the self-similar form, like so, where instead of x, we're using this this variable c, which is x minus x naught divided by tc minus t with the power alpha. And that power alpha would indicate if alpha is positive, it's shrinking solution. If alpha is negative, it's expanding solution. Okay, so now let me show you that case a equals 1/2 that basically corresponds to 2 double poles. And basically the entire solution is given like so. It's collapsing solution due to this term, 1 over tc minus t. It's second order pole, and in a self-similar form, it's given like so, with c being x minus x naught over tc minus t with the power 1/3. So it's collapsing and shrinking. So the amplitude goes to infinity, the spatial extent shrinks. So here I overlay a few different snapshots of the solution, also appropriately scaled horizontally and vertically, so that I match those maximums and minimums. And for different times, you can see that as time increases, the profile of the solution gets closer and closer to this self-similar profile that is given by, well, this black line is almost a self-similar profile. Basically, that's the shape of this center part of the solution. And the singular structure of this solution is very simple. And that's why we were able to write it out analytically completely. It's simply 2 double poles, one in the upper half plane, one in the lower half plane, located at IVC, where VC basically is a function of time that is given by a very simple dependence. It's tc minus t to the power 1/3 times some constant, VC tilde. And these 2 double poles approach the real line as t approaches tc. And at t equals tc, we have a collapse. Now, let me show you a solution for a equals 2/3. What's interesting is beyond those 2 simple cases, a equals 0 and a equals 1/2, there are no other cases where the entire solution could be given by the 2 poles of some degree. For example, when a equals 2/3, we have 2 poles of 3rd degree. But on top of that, we have additional singularities. We have branch cuts, 2 branch cuts in the upper half plane and 2 branch cuts in the lower half plane. Let me walk you through these pictures. On the left, I have the profiles of the solution again. They look similar. And again, when t approaches tc, we're approaching this self-similar profile. On the right-hand side, it's a complex singularity structure of the solution in space C, which shows the two triple poles and the branch cuts. The way we compute the solution is the following. We compute the solution on the real line, we get the data on the real line, and then we use AAA algorithm that was invented by Nick Trefethen and his collaborators that basically extends the solution from numerical data on the real line to the complex plane. And it does so through this algorithm that I can tell you more details about at the end if you want. But basically, it reconstructs the solution as a set of simple poles. And the simple poles basically can approximate any singular structure in 1D. For example, if we have triple pole, that is simulated by three simple poles that are very close to each other. And the higher numerical precision of your data is, the closer those three poles will be to each other. So basically, here we had to compute the solution with very high precision. We did it with, I think, 68 digits of precision after the dot in order to get this singular structure. Because the higher the precision you have in your data, the more poles you can reconstruct. And for the branch cuts, the branch cuts are represented by a set of simple poles that concentrate around the branching point. And by density of that concentration, you can actually judge about the power of the branch cut, of that power gamma. And the fact that these two branch cuts actually merge in a single tail is kind of an artifact of the numerical method that tries to approximate the solution with simple poles, using the least number of simple poles to recreate the solution with the appropriate precision on the real line. So basically, it's just more convenient way to do it by merging the tail for the numerical method, because that way you can achieve a given precision sooner with the smaller number of poles. But in order, again, to reconstruct this kind of picture, you should obtain the solution first with very high precision. So then came a question, how do we get the solution with such high precision? Well, one of the ways we can solve the PDE with very high precision in variable arithmetic, or we can set up an eigenvalue problem and try to solve for self-similar profile through eigenvalue problem. And let me show you what I mean about the eigenvalue problem. So if we plug this kind of ansatz for the solution in the equation, we can formulate the eigenvalue problem for eigenvalue alpha and the function f, which is self-similar profile. And this equation can be solved by so-called generalized Petryashvili method that we did. And from here, we can get two things: the self-similar profile f that I used to generate that picture for the singular structure, and we can get the value of alpha, this value for the self-similar variable here. So by doing that, we actually reconstructed the values of alpha for different values of a. And it turns out that for a less than that magical number AC given over here, the alpha is positive, and it corresponds to collapsing solution that shrinks in horizontal extent. And for a greater than AC up to 1, alpha is negative, and that corresponds to blowing up solution that goes to infinity in amplitude, but also expands because alpha is negative. And what's interesting with this generalized Petriashvili method, we were able to make it work only for positive alphas that is indicated here by green color. The rest of the alphas we had to get through the PDE, through solving the time-dependent equation. And we also got them. And for A less than AC, we were able to see that they match actually very precisely with each other. For A greater than AC, we were able to do it only using through one way. Okay, so let me quickly describe what other things we tried. We looked at the stability a little bit. We started with some random initial data and observed that it actually gets close to the self-similar profile eventually, and blowing up solution, for example, for A equals 2/3. The numerical method, I'm not going to describe it very in a lot of details, but let me just tell you that we used Fourier method, whether we worked on the periodic domain or if we worked on the real line, we additionally used the transform between x and q variable, such that if x is on a real line from -infinity to +infinity, the q variable is on the domain from -pi to pi, and we can assume periodicity if nothing happens close to the -pi and pi points. We can assume periodicity and basically solve our equation in q space as it was periodic, and also use all the techniques, the Fourier methods in q space, which we did. Now, let me show you the case when A greater than AC. So that expanding blowing up solution. So basically, if we start with some profile that originally looks, well, similar to what you've seen before, what we observe is that this solution is growing in amplitude and also expanding in horizontal extent. And in the work of Chen and Tom Hao, they actually found a result for A equals 1, very similar to ours, but they looked at the compactly supported solutions. We, on the other side, started from initial data that is infinitely differentiable always. Especially, it's good for our Fourier method. So what happens in that case actually is we start with infinitely differentiable initial data, but over time, this profile converges to something that has almost compact support. So if you see at this, if you look at this picture that shows, again, the center part of the profile that is appropriately scaled horizontally and vertically to match those maximums and minimums, you see that initially it's very smooth profile, but then eventually it converges to something that has almost a corner over here. And at the time of collapse, it forms a corner here. So basically it becomes a compactly supported solution, the one that Chen and Tom Hao found. Whereas we found a solution that actually approaches that solution when T approaches TC. And in terms of complex singularities, what we observe now, instead of the two branch cuts in the middle of the solution, we also have some singularities very close to these corners, because well, when you have very sharp transition like this, or almost a corner, that means you have some complex singularity very close to the real line. And in fact, you have two branch cuts that are very close to the real line. And that's a picture for the complex singularity structure. And you have two branch cuts very close to this, almost a corner, and two branch cuts very close to this, almost a corner. And there is also some singularity that I indicate with the red dot that sits close to the center over here that gives this kind of main profile, but it's very smooth. So those singularities are much further away from real line rather than these branch cuts. Okay, and basically this picture or this kind of solutions you get for A between AC and 1, regardless whether you have well, let me say it. So this is for real line case. For the periodic case, what happens is this expansion is arrested, and this solution does not look in this way, but basically it comes close to the size of the box and basically stops there and only keeps growing vertically. So I don't think I have a picture here in the presentation, but I have it in the paper that we published. Maybe I can show you later if you're interested in. So let me wrap up again, saying that we tried to scan this whole interval for A from -infinity to +infinity and fill all the gaps that existed in the results that were previously known. And one of our main results is that we found a special value AC, a critical transition value, on the left side of which we have a collapsing solution, on the right hand side of which we have expanding blowing up solution. And we also investigated that on the left of one, we have this expanding blow up solution. On the right, we have global existence. And for A = 1, there are two different cases where whether X is on the real line, then we have a blowing up solution, very similar to what I showed over here. Basically, that's how the solution looks like. That's for A = 1 on the real line. And for A = 1 for the periodic case, we have global existence. So basically, that solution, initially it extends, but then it's arrested horizontally, but then it doesn't keep growing actually vertically. So it exists, it doesn't blow up in finite time. And beyond 1, basically we have global existence. And on top of that, also in few of those cases, we are able to compute these self-similar profiles F with very high precision and numerically analyze the complex singularity structure of those solutions, which in some cases is quite interesting. For example, for A = 2/3, that these are 2 triple poles and then 2 additional branch cuts in upper and lower half planes. So let me just briefly tell you that there are few different ways to analyze complex singularities. One of the ways is to look at the Fourier spectrum, and by fitting the tails of the spectrum, the tails should scale like this with exponential factor and the algebraic factor. The exponential factor can tell you the distance to the closest singularity we see, whereas the algebraic factor can tell you the order of the singularity. You can extract the power of the singularity from this algebraic factor. And if some of you are interested, I can tell you more details, how it's done and why it works. And there are few other ways through rational function approximations. One of them that we use the AAA algorithm that represents the function or approximates the function through a set of simple poles using intermediate barycentric form that is given over here. And basically, it's invented by Nick Trefethen and his collaborators. And I use this method quite many times already, and I really like it. Another similar method is HGH algorithm, invented by Bradley Albert, Leslie Greengard, and Tom Hangstrom. Also very similar. For example, Sergei Dyachenko, that many of you know, likes to use this algorithm. At some point, we even compared a AAA algorithm and HGH algorithm, and they give very similar results, basically same accuracy for many cases that we compared. And there's also Chebyshev, Padé, or Fourier-Padé methods that essentially gives you a set of simple poles as well through different intermediate steps. All right, so here are the conclusions. Again, let me maybe just quickly talk through them. We look and we sweep through different parameters A, analyzing the behavior of the solutions, whether they collapsing, blowing up, or existing globally. We identified this critical value AC that is given here with all the digits that we found, such that if we're on the left of that value, we have a self-similar collapsing solution. On the right of that value, up to 1, we have expanding, blowing up solution, and beyond A equals 1, we have global existence. And we actually already published this paper in Journal of Nonlinear Science. It's also available on arXiv. And we have a few other ideas how to extend it. We could cover those gaps by tweaking our numerical methods a little bit. But also there are other ways to, other things we wanted to investigate further. For example, look at the stability of the solutions, or analyze the formation of singularities at the initial time from initial data, and look at some small amplitude solutions, because there are some analytical results or some conjectures for small initial data, and we wanted to do some numerical simulations to prove or disprove some of those claims. And also, there is an interesting transition that happens at A equals AC when we go from collapsing solution to blowing up expanding solution. And maybe we wanted to look at this transition more closely and to see what kind of bifurcation happens over there. And there's some related work into analyzing singularities. Here we only analyze singularities basically in 1D. And if somebody knows something about singularities in 2D or 3D and knows how to work with them numerically, I would be glad to hear about that, because this is something that's a question that we've been kind of bothered by a few years already, that is very useful for many other problems. And that's an interesting development where we want to actually move to eventually. So thank you for your time. If you have any questions for me, I would be glad to answer.